let's think about a capacitor. So the upper plate, let's say that is positively charged. The bottom plate is negatively charged. And suppose that you put a charge here in the middle, between the two plates. Charge Q. That charge has a mass M. And of course we have an electric field between the plates that is pointing from the positive plate towards the negative plate. Now let's assume that this charge is positive. If it was negative, the analysis will be pretty much the same. So what's going to happen when I let go of that charge at that location? So the charge is positively charged, it's going to be repelled by the positive plate on top. So the charge, ignore gravity, assume that there is no gravity here. I'm going to write it here, no gravity, because gravity obviously is also going to pull it down. So no gravity, and so the positive charge is repelled by the positive plate. So you know that it's going to move down, and it's going to move down with an acceleration because there is a force acting on that charge. The force is equal to the charge times the electric field between the plates. Now, if I were to ask you what's the velocity of that particle right before it hits the negative plate, what's the final velocity of that particle? What would you do? Well, that was a question in the homework that you just submitted, right? And the first thing that would come to mind to you is use Newton's second law. Because you have the force, you have the mass of the particle, you calculate the acceleration. So if the particle has started from, say, a distance s above the negative plate, right? Then you would say, well, the acceleration is going to be the charge of the particle divided by the mass, the charge to mass ratio, multiplied by the electric field in which it is located. And if I have the acceleration and I have the distance that the particle traveled, then I can figure out the final velocity, right? That's just kinematics. The motion is one-dimensional, so v final square, it's going to be equal to v, let's call this the initial point, and that's the final point down here. So v initial square plus 2 times the acceleration times the distance that the particle traveled. And if we're starting from rest, that's going to be 0. So that means that the final velocity is going to be the square root of 2 times the acceleration of the particle, which is q over m times e, multiplied by s. And you're done, right? That's the velocity of the particle right before it hits the negative plate. Now, what about if you wanted to look at this problem in terms of energy? You cannot, as you realized last semester, not all problems you're able to find a solution using Newton's second law, because sometimes you don't have all the precise information about the forces acting on the particle. It would be very difficult to calculate acceleration sometimes. So let's think about, for a moment, about how would you solve this problem if you wanted to do it using energy. So the first thing that you notice is that the particle is going to change, that the kinetic energy of the particle is going to increase. You're starting from rest. We said that the V initial is 0. So the initial kinetic energy is 0, right? So let's draw a line here. This was using Newton's second law. What about energy? So the kinetic energy at the beginning is 0. And you do know that the particle is going to have some final kinetic energy. It's going to be moving, so it's going to have 1/2 of mv final squared, right? And again, the question is, how much is the final velocity using energy? How would you calculate that? We do know that there is a force acting on the particle. Right? It's an electric force, which is equal to Q times the electric field. If you have a force acting on a particle and that force accelerates the particle over a distance s, what can you say about the energy, the kinetic energy that the particle has gained after the force has been acting over a distance s? We know that the force did some work, right? So the work done by that force will be equal to the integral of the force as a vector multiplied by the displacement of the particle. That's how we define the work done by a force. Right? Now the force acting on that particle as it's moving down is the electric force, and that force points down. And the displacement that we're talking about is also pointing down. Right? So that work is going to be a positive number, and since the force is constant because the electric field inside the capacitor is constant, then you can pull it out of the integral, and the result is simply F times delta S in this case. And it's positive amount of work, which means that the kinetic energy of the particle is going to increase, because the work energy theorem tells you that every time you do work on a particle, the kinetic energy of the particle increases or decreases if the work is negative, of course. In this case, the work is positive, therefore the kinetic energy is going to increase. You're starting with 0 kinetic energy, you're going to end up with some kinetic energy, so it increased. Now the parameter that I'm using for the distance, the total distance that the particle travels is S. So the work done by the force, the electric force, again, is the magnitude of the force times S, and that should be equal to the final kinetic. That's what the symbol delta means. It means final kinetic minus initial kinetic. The final kinetic is 1/2 of mv final squared. The initial, we said it was 0. Okay? So from this energy analysis, you obviously end up with the same result as before, which is that since you have that the electric force, the electric force is equal to times S, well, it's Q times E, again. Now the electric force times S, that's the work done by the electric force, is equal to 1/2 of mv final squared. So replace the electric force by Q E times S. Take the 2 here, divide by the mass, and that should be the final velocity squared. Therefore, your velocity is going to be the square root of 2Q E S over m, just like you calculated before using Newton's law. So last semester, when we did first, of course, we did Newtonian mechanics, and then we moved into energy. Some of you wanted to use Newtonian mechanics for all of the problems because you didn't see quite the point of using energy if you could find an answer using Newtonian mechanics, right? Of course, the way or the reason why we use energy is because not all the time, as I just said, you can use Newtonian mechanics. So in this case, simple case of the particle just going down, you could use either one. Of course, you get the same answer. But what about this? If you had the plate, again, positive on the top, negative at the bottom, and the particle was allowed to move, but say that it's a bead that is charged, and that red line that I drew there is a wire. So this particle is forced to move on that wire, and it starts, so the particle has charge Q, mass M, and it starts with at this location I, and it ends at this final location. And then we're wondering, what is the final velocity of the particle once it gets to this point? So then, if you want to use Newtonian mechanics, you would say, well, I need to know exactly the shape of the wire, because the wire is going to have a normal force to it, and the particle is going to be moving under the influence of the electric force and the normal force due to the wire. And if you know the exact equation for the wire, then you could perhaps figure out the normal force. And if you have those two, at every point you could calculate an acceleration, and then you could integrate that acceleration over the path and get a change in velocity. That would be extremely complicated, as you realize. So the question is, can you use, again, conservation of energy or some sort of argument about energy to solve this question? One more time, the particle is moving between two positions, and the difference in vertical location for the particle, the initial and the final location, is S. So how can we use energy for this problem? So if you're not sure about how to use energy in that problem, then let's think about what would happen if you were dealing with a particle that is under the gravitational field of the Earth. And this is your little particle m over here. And the particle is also able to move on a wire, no friction with the wire, that's important. And the particle is going to move from some initial location to some final location over here. And we're wondering what's the final velocity of the particle. And when it moves a vertical distance, say s. So how do we solve this problem using energy? We cannot, we just said we cannot use Newton's second law, but what about energy? So the answer, if you remember what we covered in 125, the answer is that you can use conservation of energy. And what you would do is you say that initial energy of the particle should be equal to the final energy of the particle, right? There is no dissipative forces here because we said there was no friction with the wire. Okay? So the initial energy of the particle is, if we're starting with initial velocity 0, then the initial energy of the particle is 1/2 of mvi squared, which is 0, plus potential energy of the particle, which is mg. We're going to set the reference level to be the f point, the final point. So it will be s for potential energy, initial. And that should be equal to the final energy of the particle. The final energy of the particle is going to be kinetic. And since we are at the reference level, it won't have any potential, gravitational potential energy. Right? So all times this particle is acted on by gravity. So the answer, again, is that the final velocity of the particle is 2, let's see. So we cancel the m with the m, and square root of 2gs. Right? So this is the approach that you would follow if we're talking about gravity. Now, can we use the same approach to solve the problem before? This is the problem that we had. The particle is acted upon an electric field, an electric force due to the presence of an electric field. At all times, that is pushing the particle down, pulling it down. That's the electric force that we have. And it is constant. Okay? So the analogy between the gravitational field and the electric field in this problem is very clear, right? It's pretty much the same problem that you're trying to solve. So because for gravity, we said that the force of gravity was constant. We said that gravity is a conservative force. And that's what allowed us to say that the work done by gravity when the particle goes from the initial to the final does not depend on whether I go following that path that you see there, following the wire, or you follow a path that is straight down and then it goes horizontally towards the final point. If this is path 1 and this is path 2, the work done by gravity following path 1 and path 2 is the same, because gravity is a conservative force. So the work done by gravity following path 1 is the same as the work done by gravity following path 2. That's the characteristic of a conservative force. Every force that is constant is a conservative force. You can, the first problem in your homework deals with that. It's easy to prove that it's path independent. The work between 2 points does not depend on the path. So that means that we can use the same approach that we use for gravity. So what was the approach that we used for gravity? For gravity, we said that the work done by gravity, when the particle goes from the initial to the final, is equal to mg times, if the particle moves through a vertical distance s, that's mgs, right? And then for a conservative force, it is true that the work done by that force is equal to the negative of the change in the potential energy associated with that force. So the negative of the change in the gravitational potential energy of the particle going from I to F is equal to mgs, right? So this is the negative of the difference in potential energy is gravitational potential energy initial minus gravitational potential energy final right? The delta means final minus initial, but you have a minus in front, so that turns things around. Initial minus final is mgs. And then the next step is to say that if the final potential energy is 0, if that's your reference level, when you're down there, you can, that's something that you can always do, set your reference level for potential energy 0 at some point that you choose. So then you say that the potential energy of a particle in a gravitational field is mgh, we call it. In this case, we're calling it s, right? So that was the approach that we followed when dealing with a gravitational force that is constant. So what we're going to do here is the same thing. And when the particle, or the charged particle, moves from location I to location F, following this path, right? What we can do is calculate the work done by the electric force in going from 1 to F, following an easy path. So the easy path would be path 2, which is you go straight down, following the force, the electric force acting on the particle. You go straight down, and then you go horizontally. Right? So what's the work? Again, this is path 1, and that's path 2. The work done by the electric force in going along path 1 is equal to the work done by the electric force following path 2. But that work is easy, because as we said before, that will be F, the electric force, times S, if you call S this distance, plus the work done on the bottom part of path 2, right? The work done by the electric forces when the particle is moving along the bottom path. How much is that work? That work is exactly 0, because the force along that path, the force and the displacement are perpendicular to each other when you're following the bottom of path 2. So the only contribution to the work between I and F is the vertical part of the path. And we calculated that that work is the electric force magnitude times S. So because the electric force is conservative, it is constant in this case, then we can say that this should be equal to some difference in electric potential energy between the initial and the final locations. And one more time, because of the minus sign, this means that you're evaluating the electric potential energy at the initial location, and you subtract the electric potential energy at the final location. So you end up with this equation then. The electric potential energy at that location I, which I'm going to call the location S, it's going to be equal to the electric potential energy at the final location. If I choose the final location to be on the negative plate, okay, on the negative plate, then I'm going to put a little minus to indicate that is at the negative plate, and you see that you have to add the term that is the electric force times S. So this is U minus plus QES. So you can associate a potential energy to a particle located in that electric field, and that potential energy is equal to the potential energy, the reference level that you have, which is the potential energy at the negative plate, plus QES, the distance. Notice that S is the distance to the negative plate, right? So a positively charged particle located between those two plates, when you bring that positively charged particle up, what is happening to the potential energy, electric potential energy of that particle? According to this equation, when S grows, the potential energy grows. So when you pull the particle from the negative plate, you're increasing the potential energy of that particle. If you let go of the particle, that potential energy starts to convert into kinetic energy, just like in a gravitational field.